Uniform electric field. Electric fields and potentials due to individual charges have been covered in an earlier unit. What is more interesting and relates to practical applications is when you have a parallel plate configuration, these two plates are parallel, with a tremendous number of charges, which we're representing by the negatives here and positives here. Just picture the whole plate covered with those charges. That creates a uniform electric field. Around a point charge, the electric field gets weaker as you move farther away from the charge. So it's very strong in here and gets weaker out here. Electric field is a vector, so if there are multiple charges, the electric fields due to each charge are added to get the net electric field. For a row of point charges instead of a single charge, the electric field behaves differently. The net electric field at any point, so let's take this point here, has a component from each of the individual charges. So for example, this guy, his electric field is contributing that. This one has an electric field, let's see, in that direction. And let's jump up here. This has an electric field in that direction. So you have to add all those together. As more charges are added in the row, there are more components that have to be added. If instead of a row of charges, there's an infinite plane of charge, and that's what we're representing here. See the dashed lines at the bottom and top? That means it goes on forever. And here's the key point. The electric field at any point would be influenced by all of the charges extending to infinity. It can then be shown that the electric field on either side of an infinite plane of charge is uniform and has the same magnitude and same direction. What we're saying is at this point, this point, this point, any point, it has the same exact magnitude. And it's always pointing in that direction. The derivation for this is a topic usually covered in calculus-based physics. The math is a little advanced for this course. If the plane is positively charged, and let's just split this down here. Over here on this side, the electric field points outward or away from the plane. If the plane is negatively charged, the electric field points inward or towards the plane. And remember, this magnitude here is the same as the magnitude here, the same as the magnitude here, the same as the magnitude here, and it's always pointing to the left. Now, let's erase this green line here. And what do you think would happen if the planes were brought closer together? So we're bringing this guy over in that direction, and this plane of the negative charges in that direction. Well, here's what would happen. The electric field to the left of the positive plane, that's this area here, cancels out. Why? Well, because the negative is giving you a field in this direction, and the positive is giving you a field in this direction. And they are both equal and opposite outside the planes there, so they cancel out. And the electric field to the right of the negative charges cancel out. All that remains is a uniform electric field between the two planes, and the contributions come from both the positive and the negative plane. So it sort of doubles there, doesn't it? So here's the result. A uniform electric field exists between any two oppositely charged infinite planes. There's the uniform electric field. The value here, magnitude-wise, is the same as the value here, the same as the value here, and it's always pointing left to right. So the electric field points from the positive to the negative plane, and it's the same magnitude everywhere within the planes. Outside the planes, the electric field is 0. Infinite plates of charge do not exist in the real world, but metal plates can be charged positively and negatively. And as long as the plates are relatively large and the distance between them is relatively small, the electric field between a positively and negatively charged plate is very close to being uniform. And once again, a uniform field means it has a constant magnitude and direction, which is why these lines are shown equally parallel to each other. They have the same length and they're all pointing in the same direction. And now, how is it infinite? Why can we model this on an infinite plate? Well, it's kind of like the Earth, right? We know the Earth is round, but if you're standing in a field somewhere, you can only see so far, and it really looks like it's flat. So you're modeling the Earth as a flat surface there, even though it's round. So if you have two plates that are very large and you're very close together, if you're inside there, which you're not, it looks like those plates go on forever. So we can model it as a uniform electric field between the two finite size plates. So let's compare our two configurations now. Point charges have a non-uniform field strength since the field weakens with distance. Also, the electric field is non-uniform in direction. It points in many different directions. A uniform electric field points in the same direction, has the same magnitude everywhere. Only some equations from the previous units will apply to uniform electric fields. For the parallel planes, the electric field is generated by the separation of charge. You've got all positives up here and all negatives down here. The field lines originate on the positive charges and terminate on the negative charges. The difference in electric potential, voltage, is responsible for the electric field. The change in voltage is defined as the work done per unit charge by an external force against the electric field. We did that a few topics ago. Therefore, energy is being put into the system when a positive charge moves in the opposite direction of the electric field. So here we have a positive charge and it's moving this way against the electric field, which means somebody's applying an external force to it. It's also the same when a negative charge moves in the same direction of the electric field. Positive work is being done by the external force, and since the positive charge is moving opposite the electric field, negative work is being done by the field. A useful equation relating voltage in a uniform electric field can be derived. The electric force on a positive charge released in a uniform electric field is constant. Therefore, the work done by this field is WE, and E stands for electric field this time, not external. External would be EXT. So the work is F delta X, and the force is just QE, delta X. Since the electric field is conservative and work done by this field is equal to the negative change in electric potential energy, we have this expression here. And then, what's delta UE? Why, that's Q delta V. So we have work done by the electric field is minus Q delta V. The same electric field force is performing work. It's just expressed in two different equations. We're allowed to set the two of them equal to each other. So we have work is QE delta X, and work is also minus Q delta V. Set them equal to each other. We have QE delta X equals minus Q delta V, and we want to solve that for E. So first we divide through by Q, and they cancel out, and then we divide through by delta X. And we have E is equal to minus delta V over delta X. We've already shown this graphically, but now we're showing it in an equation. And what does that tell us? The negative sign indicates that the electric field lines point in the direction of decreasing electric potential. When solving these problems, we're frequently only asked for the magnitude of the electric field, so we don't need to worry about the negative sign. But just remember, that negative sign tells you which way the electric field is pointing. It's pointing in the direction of decreasing electric potential. This equation only applies to uniform electric fields. It follows that the electric field can also be shown in terms of volts per meter. Why? Well, this is volts, this is meter, in addition to newtons per coulomb. Let's see why that works. So we have volts per meter, and what's a volt? Well, that's a joule per coulomb. Now we're dividing that by M. A joule per coulomb over meter, well, a joule is a newton meter. So we have newton meter divided by coulomb over meter. What do we have next? We have the newton meter over coulomb. Well, divided by meter, the meters cancel out, and we wind up with newtons per coulomb. The units are equivalent. So volts per meter, same as newtons per coulomb. What voltage should be applied to create an electric field of 1200 newtons per coulomb between two plates which are 3 millimeters apart? We start by listing our givens. Here's the electric field, and here's the separation distance, and we have to convert millimeters to meters. So 1 millimeter is 10 to the minus 3 meters. We have our uniform electric field equation. The voltage is equal to minus E delta X. We substitute in our givens, and we get 3.6 volts. Now don't worry too much about the negative sign. That refers to the direction of the electric field, which we're not asking about, so we can ignore it when solving for delta V. What is the magnitude of the electric field between two metal plates 5 millimeters apart if the potential difference between them is 110 volts? We have a potential difference of 110 volts. Here's the distance between the plates, which we convert to meters by moving the decimal place 3 places to the left. Have our equation for the uniform electric field. Now we want the absolute value of E, okay, because we want the magnitude, so we'll find the absolute value. So the absolute value of E is minus delta V over delta X. We divided both sides by delta X. Substitute in our givens, and we get an electric field magnitude of 2.2 times 10 to the 4th newtons per coulomb.